In this lecture, I will share how to derive equations of uniformly accelerated motion by using calculus method, that is by differentiation and integration. First of all, let me take the first equation, that is v equal to v naught plus at. We have to prove this equation where v naught is speed of body at time t equal to 0, v is speed of body at any time t, and a is value of constant acceleration of the body. In order to prove this relation, let us consider the definition of acceleration. Acceleration is defined as rate of change of speed of body, that is a equal to dv by dt. So this can be rewritten as dv is equal to a into dt, that is just by cross multiplying. Now we shall integrate both sides. Integration dv equal to a is constant, it can be taken out of integration. Now we have to put the limits of integration. On right hand side it is integration with respect to time. So starting time is 0 and final time is t. Corresponding to these limits, we have to put limits on left hand side also. It is integration with respect to speed. So what is speed at t equal to 0? That is denoted by v naught, and at time t speed is denoted as v. So we have to solve this integration. Left hand side will be, answer will be v, limits v naught to v. On right hand side integration will be t, and we are having limits 0 to t. After applying the limits, we can write v minus v naught equal to a t minus 0. So after simplification, we can get v equal minus v naught equal to a t. This will give us v is equal to v naught plus a t. Hence the required relation by using differentiation and integration, that is calculus method. Second equation of motion is s equal to v naught t plus half a t square, where s represents distance covered by body in time t, a represents constant value of acceleration, v naught represents speed of body at starting time t equal to 0. Now how to prove this by calculus method? For proving this equation, let us consider the definition of speed. As we know, speed is defined as rate of change of position coordinate with respect to time. This will give us dx is equal to v dt. Using first equation on right hand side, that is, we can put v equal to v naught plus at on right hand side. So we can write dx is equal to v naught plus at dt. This equation can be written as dx equal to v naught dt plus a t dt. Now we shall integrate both sides. After integration, on left hand side we are left with integration dx. On right hand side, first term becomes integration dt. V naught is constant initial speed, it can be taken out of integration, plus a is constant acceleration t dt. Now we have to put the limits. On right hand side, starting time is 0, final time t. Similarly here 0 to t. Corresponding to these initial and final values of time, we can write coordinates of position x0 and x. Now we have to solve this integration. On left hand side answer will be x and limits x0 x equal to first integration is v0 t limits 0 to t plus a integration answer will be t square by 2 limits 0 to t. After applying the limits, we can write x minus x naught. On right hand side, v naught t minus 0 plus a t square by 2 minus 0. Now x minus x naught can be replaced by s, that is distance traveled. This is initial position, this is final position. Difference of the two will give us distance covered by the body in time t. Right hand side we get v naught t plus half a t square. Hence the required second equation of uniformly accelerated motion. Now let me take the case of equation number 3, that is v square minus v naught square equal to 2as, where symbols again have the same meaning as discussed in earlier two cases. For proving this equation, let me consider the definition of acceleration, that is equal to rate of change of speed with respect to time. A is equal to dv by dt. Multiply and divide by dx only on right hand side of this equation. I can write A is equal to dx by dt multiplied with dv by dx. I have multiplied by dx and also divided by dx. This can be written as A is equal to v, because dx by dt can be replaced by v into dv by dx. This will give us, after cross multiplying, v dv is equal to a dx. Now we have to integrate both sides. Integrating, I can write v dv equal to a taken as constant dx x naught x. Corresponding to these values, speed initial is v naught, final is v. Integration of left hand side gives us v square by 2 limits v naught v equal to a. Integration on right hand side gives x, limits are x naught x. After simplifying, left hand side becomes v square minus v naught square multiplied with half is equal to a x minus x naught. Now x minus x naught can be replaced by s, distance covered by body. After taking this 2 to right hand side, we can get our required equation v square minus v naught square equal to 2as. Hence the required third equation of uniformly accelerated motion. That's all.